Hello, my name is Maxim Figat, and today I would like to present you a short introduction to the Robotic System Design Methodology. I'm an assistant professor at Warsaw University of Technology and currently a visiting postdoc at Jet Propulsion Laboratory. My presentation will start with the motivation. So let's imagine that we want to build a robotic system. It requires a lot of performing different tasks from different development phases. And this presentation will focus mostly on specification determination and implementation. Since this subject is a little bit complicated and complex, the presentation will be divided into two parts, and I will start with the introductory part with basic concepts, and I gradually will increase the complexity of the presentation, switching to the second part. So what's the first motivation? So the first motivation is that I want to bridge the gaps between the requirements and implementation. So let's imagine we have a young robotic system developer who starts his journey with the definition of the requirements, and then he thinks that when he will reach the requirements phase, then he will switch directly to the implementation phase. But finally, he realizes that between those two phases there is an implementation gap, and either he has superpowers or he has appropriate super tools. However, not all of the developers have appropriate tools, so we usually use publicly available tools. But whenever a new version of the tool appears, some problems with our robotic system development process can appear. And what we need a strong foundation of the specification, which is the results of the robotic system modeling phase. But when we introduce it, in fact, we introduce another two gaps. We call them specification gaps. So what we need in fact to build appropriate bridges between requirements and specification and implementation. When we build those two bridges, we can reach finally the implementation. So the main goal of my research is in fact focusing on the definition of the appropriate formal specification and providing appropriate tools which facilitate switching, traversing through those two gaps from the requirements through the specification and finally reaching the implementation phase. Another motivation is the problem with the diversity of robotic systems. So let's imagine we have a simple robotic system that we want to develop. It consists of 4 motors and 4 wheels and a camera. And when we finally develop such system, we are asked to develop another system that is in fact extended version of it by a manipulator. And then we are asked to develop a new robotic system which provides a mast with camera and a camera attached to the manipulator. But what happens when we are asked to develop 2 other robotic systems with different locomotion systems, like rocky boogie system or legged robots? Or maybe it will be a flying robot. Or maybe it will be a multi-robotic system consisting of 3 robots working in formation. So there are different questions that we can ask. So do we in fact need to develop every robotic system from scratch, or maybe we can find some common concepts across different systems and typically, as in computer science, reuse some already existing elements of already existed and created systems. And what in fact we can find, what those systems they have in common. So each robotic system operates in an environment. It uses sensors to perceive the environment. It uses actuators to interact with the environment. it has defined task and a mission. It has some skills and abilities derived from the capabilities of the sensors and effectors, and it uses those skills to perform the plan by performing actions. And each of the robotic system also has the architecture which describes both the structure and the activity of the robotic system. And those concepts, not all of them, because there are many more systems, all of those concepts, in fact, they form the concept of ontology for robotic systems. So in fact, ontology defines the abstract concepts used to define robotic system and relationships between those concepts. Another goal of the research is to provide appropriate ontology for robotic system and guidelines for designing robotic systems. And those guidelines we call patterns. So what we want to do, we want to develop a robotic system pattern which is parameterized by different parameters based on concepts from the ontology. So let's imagine a very simple example. Let's imagine that we want to buy a car. So whenever we want to buy a car, we have to go to the dealership, car dealership, and we are asked what color of the car we want to buy, what other parameters our car should have, like engine, what model, what the drive system, and so on. So in fact, we are asked to provide appropriate parameters to the general car pattern, and based on this pattern, a car is generated by the factory, and we can enjoy driving a car in a few months, like in 3 months. But we can also look at the same problem from different perspective. We can look at the picture on the left side here as a parameterized car meta model, which is parameterized by different parameters. And when we specify those parameters, we obtain we obtain a model of the car. And then this model can be utilized for a generation of the real car or verification of some properties of the system. So the general idea of my research is in fact focusing on providing the parameterized meta model for the robotic system and providing appropriate parameters which together will be the input to the robotic system model generator. And when the generator finishes its task, it creates a model of the robotic system, so both the structure and the activity. And then this model can be utilized to analyze the properties of the system and to generate the code for the system. The second presentation is divided into 6 parts. So the introduction will be focusing on the methodology and the meta model. Then we will focus on the specification, analysis, tools, and conclusions. So let's start with the methodology. Our methodology, called Robotic System Specification Methodology, consists of 4 different layers. The first layer forms the ontology based on embodied agent concepts. So in fact, it defines concepts necessary to define the structure of the system and to define its activity. And based on those concepts, we can define robotic system meta models. And in our approach, we utilized 3 different meta models. One was focusing on hierarchical finite state machines, another based on Petri nets, and the third one on the domain-specific language. Based on those meta models, we can create a model, and then based on the model, we generate a robotic system controller code, either semi-automatically or automatically. So let's focus now on the robotic system design methodology, which extends, in fact, the robotic system specification methodology. So everything what was done before, in fact, is contained within this black box. So we can look at our previous research from the perspective of the black box, which has appropriate interfaces, input interface and output. So as an input, it takes the specification defined in robotic system specification language, and as an output, it generates the controller code, which can be further deployed on the robotic system. So in fact, in this article that we are presenting, that we are submitting, the main contribution is presented here on the left side. So this is the introduction of the robotic system ontology and transformation of the general requirements into the specification. So what we in fact provide, we provide appropriate patterns that define and that help the designer to define the specification. Because currently our previous research required from the designer to provide appropriate specification, but our previous research didn't answer the question how to provide a specification. What exactly, of course, it said what parameters should be provided, and we explained how those parameters can be presented in the robotic system specification language, but we didn't answer the question how to define those parameters, how to obtain them based on the requirements. So our contribution of this article is presented here on the left side. Let's start with the ontology. So since the ontology is divided into the structure and activity, we'll start with the structure. So each robotic system is in fact decomposed into collaborating with each other agents. Because agents, they can communicate either directly through the transmission mechanisms or through the environment. So one agent perceives the environment with receptors, and based on the data from receptors, it provides the commands to effectors to change the state of the environment. Control system is responsible for making decision based on its current state, and based on the inputs from other agents, and based from the inputs from the receptors. Whenever we remove from embodied agent appropriate elements like receptors, effectors, transmission buffers, then we can obtain different agent types which in fact have different tasks. They perform different tasks and they have different responsibilities within the system. But embodied agent has a little bit more complicated structure. So the control system that I already presented on the previous slide is in fact defined as the set of 3 different types of subsystems. Control subsystem, which is responsible for making decisions based on data from receptors and making and defining commands for the real effector. We also introduce virtual receptors and virtual effectors, which in fact translate low-level data to high-level data. So from the perspective of receptor, so let's imagine that we have a camera that provides an image. An image is acquired by the real receptor and provided to the virtual receptor. And instead of sending directly the image to the control subsystem, the virtual receptor extracts the most important informations from the image. For example, extracts position of the object that we are tracking. And since the control subsystem can communicate with many different virtual receptors, because we can have 5 cameras or dozens of different sensors. In real systems, we in fact have many different sensors. It would be not necessary. It wouldn't be the best choice to send to calculate all of the input data within the control subsystem. It would be much better if the control subsystem only receives the information directly calculated and appropriately extracted by virtual receptors. And instead of sending directly, and based on those data, control subsystem can calculate the command for the real effectors, like for the motors. But instead of sending directly PWM or current, it operates on much higher layers. It defines, for example, the end effector position. So it calculates where the end effector should be within a given time window. And then it provides this information to virtual effector, and the virtual effector transforms the commands received by the control subsystem in order to control the real effector appropriately. Each subsystem consists of the input buffers. Here is the input buffer, and output buffers. Input buffers are necessary to collect data received from other agents. Output buffers are necessary to send data to other subsystems. Also, subsystems, they contain internal memory, which represents the current state of the subsystem. Now I will give a short introduction to activities of robotic systems. So each robotic system is decomposed into agents into subsystems, and the task of the subsystem, in fact, is defined by the set of behaviors and appropriately connected with each other. And whenever a subsystem performs its task, it activates a given behavior, and the behavior, in fact, is decomposed into several subsequent steps. So at the first state, behavior calculates transition function based on the input buffers and based on the current state of the subsystem. It calculates the new state for the subsystem and the new data for the output buffers. And then it sends the data from the output buffers to other subsystems. It waits for a while, and then it receives data, and the received data are saved within the input buffers. And then it checks two conditions. One is the error condition, and one is the terminal condition. If any of those two conditions are fulfilled, then the subsystem stops performing the behavior, like here, and switches to appropriate subsequent behavior. In this case, on the left side, we have a simple automaton, finite state automaton, where behavior switches automatically because there are no other possibilities. So from S1, we switch to state S2. And we activate behavior 2. But when none of those conditions is fulfilled, then the behavior iteratively performs subsequent steps. So it starts again with the transition function. In our approach, robotics, the whole robotic system is in fact set of subsystems interconnected with each other, and they are connected by the communication channels, and each channel has the sender and receiver. Sender sends data in one of three different communication modes: blocking with timeout, and non-blocking. And receiver receives data also in three different communication modes. So in fact, for a pair of communicating subsystems, we can get up to 9 different communication models. So let's focus now on the different modes from the perspective of sender. So when the sender performs its activities in non-blocking mode, it means that it's after the calculated data, when it finishes calculating new data within the output buffers, it sends them, and then it performs its other activities. In a blocking mode, whenever it sends data, then it waits until it receives the confirmation. And since the confirmation may not appear because the receiver, since there can be some error with the receiver, some problem with the receiver, the sender may wait endlessly. So it will block the system and the deadlock can appear. And it's very dangerous. So we can also introduce we can also use blocking mode with timeout. So whenever the subsystem sends data, it waits for the confirmation for a specified time, and subsequently, whenever the time elapses, it stops waiting and activates then other activities. Now we know the basic concepts from the ontology, so we have to ask ourselves how those concepts can be somehow translated and used to define the specification. How we can define those parameters that I already mentioned. So we prepared within this article, we focused on introducing patterns and guidelines patterns from perspective of 4 different stages. So stage where we define requirements, specification, implementation, and deployment. In fact, this article focuses mainly on the specification and treats other layers as the layers which influence the specification. And since this topic is quite complicated, please read the article about that. And this presentation only I wanted to prepare this presentation in order to give you a general point of view, a general perspective of our research. And everything about the guidelines is within the article. And this is just the slide which presents some of the most important tasks that we have to do within those 3 development phases, so where we define requirements, structure, and activity of the system. I have connected different elements with the by the arrows, by the edges with arrows, but this is just the proposed and utilized by me direction. It doesn't mean that all of the steps should be performed within this direction, because as I presented here, whenever we define a system, in fact, we need sometimes to come back to the previous states, because at the beginning we don't want to specify the whole robotic system based on the requirements from A to Z. Probably we want just to prepare a blueprint, the general structure and general activity of the system, and then perform all of the steps, so implement, verify whether everything works, deploy on our system, and then gradually we increase the complexity. We increase also some requirements, because otherwise this task will be not possible to finish. Our core element is in fact a parameterized meta model, and we are using a meta model which is based on PetriNets. And since PetriNet is the crucial element of within our approach, I will give a short introduction to PetriNets. So PetriNets are usually very good tools to model the systems, synchronization and concurrency and communication for systems. And they are also very good to analyze properties of the system. So let's assume that we will start with the bottom picture. On the left side of this bottom picture, we have a producer, a PetriNet which defines the activity of producer. And on the right side, we have a definition of the activity of consumer. PetriNet consists of 2 different elements connected with each other using edges with arrows. So rectangles are transitions, large circles are places, and within places we can have tokens. The token is the black dot. And with transition, we can associate operations, activities. We call it firing activity. A transition can fire whenever an appropriate number of tokens within the input place, this is the input place of this transition, resides within the place. So this edge has the weight 1, because by default, whenever there is no value associated with the edge, it means that its weight is 1. It means that in order to enable this transition and make it fire, it requires a single token from the input place. Whenever it fires, it produces a single token within the output places. Those are 2 output places, and the token appears here and here. And because token appears here, this transition is enabled, it can fire. But also another transition is enabled, transition from the side of the consumer. So since 2 transitions are enabled, we don't know exactly which transition will fire. But let's assume that the transition on the left side will fire. So this transition fires, it consumes token from here and produces here. So this is the state. And remember that the positions of those tokens within places, in fact, they define the state of the system. And by moving those tokens and firing transitions, we change the state of the system. And in this case, we will fire the transition associated with consumer. So this transition fires, it consumes the token from here and from here. This transition fires, it consumes both tokens. Then it produces here a single token here, and this transition is enabled. But what will happen if producer performs its operations with higher frequency than the consumer? So producer definitely will produce more data and faster, and then the consumer can consume them. And in fact, it can lead to the buffer overflow problem. And in order to solve it, we can introduce an additional place in which we have 4 tokens, which represent the how many elements within our buffer are free. So how many data producer can produce. So whenever the producer produces all of data, we consume all of the tokens from this place, and the buffer is full. And introducing this place, in fact, we synchronize producer with the consumer. And then the consumer can consume data, and producer will produce a single data, and now they will be synchronized. And now I would like to give a short introduction to the hierarchical Petri net that I introduced within the research in my PhD. So instead of places and transitions, we additionally have pages. So with the double circles, it's a double circle. With places, we associate operations and tokens. With transitions, we associate conditions and priorities and timeouts. And with pages, so with them, we associate other Petri nets. So let's focus how the hierarchical Petri net works. So whenever we have 2 transitions enabled, one has the priority, higher priority, so it will fire before transition T1. We don't want to have such situation when we don't in fact know which transition will fire, because we want to have a deterministic system. So in order to introduce the determinism in our system, we introduce also priorities. So whenever the 2 transitions can be enabled, we introduce the priority to the second one, and it will lead that in fact this transition will fire. So what does it mean? Whenever transition T2 fires, it consumes tokens from input places, and it activates the operation associated with the output place of the transition T2. And whenever the operation finishes, the token appears within this output place. But let's focus now how the transition firing works in hierarchical Petri net. So let's assume we have a very simple Petri net which has the page. So inside this page we have additional Petri net with a single input place and single output place. Whenever we fire transition T1, in fact, we produce a single input token, we produce a single token within the input place, and we activate additional transition which can fire. But from the perspective of output Petri net, the hierarchical Petri net, in fact, it means it looks like that. So the Petri net is activated. It performs some activities. And after a few steps, whenever the transition T22 fires, it produces a token within its output place, and the transition T2 is enabled because from the perspective of higher layered Petri net, the token appears within P2. This is the short introduction to notational convention. So the base idea is that we have central symbols here, so places, pages, transitions, hierarchical Petri nets, conditions, priorities. We have list of different names. So J defines the name of agent, the V name of subsystem, W name of behavior, and so on. And list of keywords on the right hand side top defines different layers. And I have introduced within my research the hierarchical Petri nets, which are in fact 6-layered Petri net. There are 6 layers, and Petri net has appropriate properties. It fulfills the properties such as it's safe, it has no deadlocks. In each low layer Petri net there's a single input place and single output place, and in fact they are decomposed into very simple and straightforward Petri nets, which enable, in fact, ultimately enables us performing analysis of the whole Petri net, as it was presented in 2022 in our paper, in RAS paper. So let's activate the Petri net and let's simulate it just to understand the layers. So we have the input, within the input place we have a single token. Whenever transition T1 fires, it activates the pages, so hierarchical Petri nets, which are on the lower layers defined. So not only we have layers, but within each layer we have panels. So in the first Petri net we have 2 pages, and let's assume we have 2 pages because there are also 3 dots. But let's assume we have 2 pages, so it means that we have 2 panels within the lower layer called agent layer. So agent layer defines, maybe I will start with the first layer. First layer defines the whole robotic system as the decomposition of the system into agents. So in fact it defines the activities of agents, and Petri net from the agent layer defines its activity. But the agent in fact is decomposed, as you remember, into subsystems. So whenever it performs whenever it fires transition T1, it activates its subsystems, activities of its subsystems, and then we switch here. Token appears within the input place, and the transition T1 is enabled and can fire, so it fires, activating behavior of the given subsystem. So the token appears here, and we can perform the activities within the behavior. So we start with the transition function. I will omit everything below because it's complicated. I just want to give you a short and general point of view. So whenever transition function is performed, then a token appears here, and the transition T2 is enabled and can fire. And after a few steps, finally we send data. We send data. We wait for a specific time in order to because we want our subsystem to work with a given frequency, and then we send data. And whenever we finish both sending and receiving data, we have to check two conditions. So the first condition is error condition and terminal condition. If both of them, if one of them is fulfilled, then we have to stop the behavior. Otherwise, we iterate within the behavior. So if none of them is fulfilled, whenever one of them is fulfilled, we fire transition T6. A token appears in output place here, and from the perspective of higher Petrinet, a token appears here, and it activates transition T3. And now we can switch to another behavior, and we can perform another behavior. So we activate behavior omega prime, and the token appears here, and everything is repeated. Of course, on the lower layer, we have two other sublayers. So on the left side, we have two sublayers defining the decomposition of transition function into partial transition function, so based on the output buffers. And each of the partial transition function is decomposed into overloaded transition functions based on the availability of data within the input buffers. Here on the middle, we have a definition of the communication of the subsystem V. So subsystem sends data. So it defines the first layer defines the arrangement, so in which how the subsystem communicates with other subsystems. So it can send data in parallel or sequentially. So we can define the Petrinet Petrinet which model the sequence of sending data. And here on the bottom, it defines the activity of sending subsystem. On the right hand side, in fact, this column defines the arrangement from the perspective of receiving data and communication model from the side of the receiver. So those two layers, in fact, when we combine them from perspective of two communicating subsystems, they form a general communication model, which is parameterized by two parameters, timeout1 and timeout2. By appropriately defining and selecting those two, selecting values for those two parameters, you can obtain up to 9 different communication models. So whenever timeout1 is equals 0, so this is 0, and timeout2 here is 0, it means that whenever our subsystem finishes calculating data, so we have new data, we want to send data, so we activate this or this transition function. We activate one of those two transitions based on whether the data has been already received or not by the receiver. And here we fire one of those two transitions. This transition has higher priority, and based on the information whether the data was received, so whether the confirmation was received by the sender or not, either we are blocked, either we fire the transition T6 when the confirmation was received, or we are blocked on T5 transition. But since timeout1 is 0, we can fire this transition without waiting. So by introducing timeout 1 equals 0, it means that we can simulate the non-blocking mode of the sender. And by introducing timeout 1 equals infinity, we'll be waiting here endlessly until the data will be received. And similarly, from the perspective of receiver, whenever timeout 2 is 0 and we are ready to receive data here, but the data are not provided, so we fire this transition and we update the information within the state of the subsystem. The data were not available, and this information can be crucial for real-time or hard real-time systems, and we perform some other activities. For example, we stop performing a behavior and we react appropriately because maybe it's a huge problem for the system. And now we have to answer the question, whenever we already have the meta model, how we should define the parameters and what parameters we should define in order to obtain the model of the system. So we defined a set of different parameters that should be defined. And now there is a question how those parameters should be specified in order to translate those parameters, some abstract parameters, into the controller code. Yeah, so we have the parameterized meta model, we have the specification. So how? So we introduced a robotic system specification language in 2022 in journal RAL. This is the domain-specific language, which is used to specify multi-agent robotic systems. It is based on the ontology, and it facilitates the definition of the structure and the activity of the system. This is the example of definition of parameters for some of our systems that we have developed. So it defines the structure. Here we define the agents, and here we define the subsystems for a given agent ball collector. Here we define the communication means within subsystems within the agent BC, and here we define the intercommunication channels. Here we define the types and buffers for another agent, and here on the right hand side we define the activity of one of the agent. We also developed tools because without tools nothing will work. So we created a robotic system specification language compiler which performs 3 different analysis tasks. So it performs lexical analysis, syntactic analysis, and semantic. So the semantic is very important because it already helps the developer to remove some, to find some problems in the specification. So we cannot allow to have two agents with the same name, for example. And then the model, when the specification is correct, then we automatically generate the RSHPN model, and the model is loaded to the RSHPN tool that I have developed. And this tool also enables the developer to define Petri nets by hand, so manually. But since the Petri nets are complex for real robotic systems using our approach, definitely Petri nets should be generated automatically. They are generated automatically. And you can here define different elements. You can add buffers, you can define types, data types, you can define behaviors, and you can define even the associate activities with each place, and you can generate code. So the general pipeline within our approach was that we provided the RSHPN meta model, we provided robotic system specification language, and the compiler generates automatically hierarchical Petri nets, and those files in a form of two different sets of files, and those files are loaded by the RSHPN tool, and the tool generates either C++ or Python code for robot operating system, and it also was used to generate C++ code interpreting hierarchical Petri nets. To conclude, we verified our approach based on different robotic systems. Here I present only 4. So for ball collecting robot here, and for the 7-degree LW airfoil plus manipulator, we developed the whole controller using our approach. For those systems, we developed only the task, because lower layer controller was already developed within our team. To sum up, we defined the robotic system specification methodology based on model-driven engineering approach. We introduced parameterized robotic system hierarchical Petri net meta model, appropriate tools, so both the tool for Petri nets and domain-specific language. We verified everything on different experiments, and we provided the guidelines how to define those parameters based on the requirements, and we also defined how to decompose how to translate the general idea of the task, the robotic system, into the requirements, and how those requirements can be translated into the parameters of the input parameters for the parameterized RSHPN meta model. Those articles present the results of our research. In robotics and automation letters, we provided the definition of the robotic system specification language. In robotics and automation systems, we defined the meta model based on hierarchical Petri nets, which is parameterized, and we define the parameters. And within others, we acquired appropriate experience, which led us to those 2 main contributions, to main articles. And based on the whole experience, based on those articles and other projects and other experiments, we defined appropriate guidelines and ontology for defining the specification based on the structure and activity, so the architecture for the robotic system.